This is Richard. He's an electrician and a professional physician. Now you may be wondering, what does his job professions have to do with this?
Because in today's lecture, we're going to be talking about
Richard's Lectures! Today's lecture, Photoelectric Effect! Brought to you by Prix. It has the shape and color of science.
Hello, my students. I am Mr. Dr. Professor Richard, and I'm going to give you this week's lecture. Let's start things off with terms. 1. What's a quantum? Well, to be honest, today's lecture was about to be a quantum phenomenon, but since it was so confusing and it felt like watching the movie Inception, I chose photoelectric effect instead. Quantum is actually a unit. It shows how much physical entity is in an interaction. So if you still don't know quantum, then let's have an example here. Say you have a George right here. And then you want an interaction of 10 cents. How much do you really need to get 10 cents from George? Well, that'll be 90 cents. So you get 90 cents and you cut it with the George, and then you get 10 cents back. Well, so now that we're done with the quantum and talking about quantum stuff that I don't even need to talk about in this lecture at all, we're going to talk now about photon. Photon, unfortunately, is a quantum of light. Now that we know what a quantum is, and that a photon is a quantum of light, we can now discuss about the photoelectric effect. And now, class, I'll read to you all about the details of the photoelectric effect. The photoelectric effect. Now I'm going to demonstrate to you about the photoelectric effect with some neat tricks. So you got your whole atom here. I'm not gonna say which atom it is. And here's like your protons and nucleus right here. And here's your electrons right here. I'm not discriminating anything since the electrons are already yellow. And over here we got a photon. I don't know why this photon is dark. So this photon over here is just gonna go and collide with this one. And then let's just say that if it's strong enough, and let's just say, if you believe in yourself hard enough, you'll fly off. I believe I could fly. Actually, another interpretation is,
See you later, suckers! And then he lives happily ever after.
Gosh. So you may be wondering, why did that electron act like a total rock star? Well, you see, in a very confusing equation we got here, we need a rainbow! Now first, before we talk about how this is related to the photoelectric effect, we are gonna have a side lesson! Now there was some time in the class that you learned about the electromagnetic spectrum. The sunlight that we have is radiation. The microwave used to cook our food has radiation. This X-ray is a radiation. You know that it starts from red all the way to purple. And that red is radio, and the purple one is gamma rays. The strongest of the electromagnetic radiation so far. Why is it strong? Because as you go down the electromagnetic spectrum, the frequency increases, but the wavelength decreases. Photons come from different radiations, and depending on the radiation's frequency and the electron, it can be observed whether or not there will be a photoelectric effect. Oh duh, that's why I had that dark blue tricks. I don't know why this photon is dark. Because since the blue is much more powerful than yellow, green, or red, judging by its frequency, it was able to move that electron that we had observed in our experiment. And for this next part of the lesson, I'm gonna go more slowly. Be right back, my students. I have returned, my students. And now for this next part of the lesson, we'll be talking about the history and equations of the photoelectric effect. I am live. Let's start! In 1887, Heinrich Hertz observed the photoelectric effect and the production of the reception of electromagnetic waves. Now that this very man had used his last name as a unit for observing and measuring voltage and electricity. He published these observations in the journal Annalen der Physik. His receiver consisted of a coil with spark gap, where a spark would be seen upon detection of electromagnetic waves. He placed the apparatus of a dark box to see the spark better,
However, he knows that the maximum spark length was reduced when in the box. A glass panel placed between the source of light electric waves and the receiver absorbed ultraviolet radiation that stimulated electrons jumping across the gap. When removed, the spark length would increase. He observed no decrease in spark length when he substituted quartz for glass, as quartz does not absorb UV radiation, since it is an opaque material. Hertz concluded the months of his investigation and reported the results obtained. He, however, did not further pursue investigation of this effect. Then we move on to 1905! Our favorite German, Albert Einstein, saw the apparent paradox by describing light as composed of discrete quanta, which quanta is the plural of quantum, now called photons, rather than continuous waves. Based upon Max Planck's theory of black body radiation, Einstein theorized that the energy in each quantum of light was equal to the frequency multiplied by a constant, later called Planck's constant. A photon above a threshold frequency has the required energy to eject a single electron, creating the observed effect. This discovery led to quantum revolution in physics and earned Einstein the Nobel Prize in Physics in 1921. By wave-particle duality, the effect can be analyzed purely in terms of waves. Einstein's mathematical description of how the photoelectric effect was caused by absorption of quanta of light, now called photons again, was in one of the 1905 newspapers named On a Heuristic Viewpoint Concerning the Production and Transformation of Light. This paper proposed a simple description of light quanta, or photons, and showed how they explain such phenomena as the photoelectric effect. This simple explanation in terms of absorption of discrete quanta of light explains the features of the phenomena and the characteristic frequency. Einstein's work predicted that the energy in individual ejected electrons increased linearly with the frequency of the light. Perhaps surprisingly, the precise relationships had not at that time been tested. By 1905, it was known that the energy of photoelectrons increased with increasing frequency of incident light is independent of the intensity of the light. However, the manner of the increase was not experimentally determined until 1914 when Robert Andrews Millikan showed that Einstein's prediction was correct. The photoelectric effect helped propel that the emerging concept of the dualistic nature of light. That light simultaneously possesses the characteristic of both waves and particle, each being manifested according to circumstances. The effect was impossible to understand in terms of classical wave description of light, as the energy of the emitted electrons did not depend on the intensity of the incident radiation. And now that discovery helped us see more understanding and discoveries today in our personal lives. And that is the photoelectric history. Hey, Richard. Yes, Richard? I believe it is time for something. You are correct, Richard.